lesson video for Honors Chemistry for section 19.1. And as always, if you want all my videos in one place, just subscribe to my channel. So chapter 19 is on acids, bases, and salts. So today in section 19.1, we are going to focus on different definitions and properties of acids and bases. So acids have a sour taste, change the color of an indicator, can be strong or weak electrolytes in aqueous solution, and react with metals. So when you eat something sour, like a lemon or like Sour Patch Kids, that's usually from citric acid that has been added. When you throw up, it tastes sour because your stomach acid is hydrochloric acid. If you've ever used like litmus paper, the little pH paper that you dip in, the little strips that you dip into different substances and they'll change colors, those have been soaked in an acid-based indicator, so they'll change the color of an indicator. They can be strong or weak electrolytes. Remember, electrolytes conduct electricity. So acids can be strong electrolytes, which conduct really well, or weak, which conduct poorly, but will conduct a little bit. And then they react with metals. Depending on the concentration of the acid and which metal you dip into it, some acids will completely corrode and eat away a metal. So the metal will dissolve into ions inside of the acid. So bases, on the other hand, can taste bitter. An example, because a lot of bases we don't eat, a lot of bases we use in cleaners and things like that. But unsweetened chocolate has a base in it. I mean, sweetened chocolate does too, but the sweetness of the sugar that's been added hides that bitter taste. So if you really want to know what bitter is, if you're not actually sure what it means, because a lot of my students, they equate it with being sour, but it's not, just buy some unsweetened chocolate and take a bite, chew it a little bit, and you'll know immediately what bitter is. It will also change the color of an acid-base indicator, but clearly a base would change it a different color than an acid would. And then they can also be strong or weak electrolytes when dissolved in aqueous solutions. So next we're going to move on to some definitions. Now we focus on 3 different definitions for acids and bases, and each definition focuses on a different aspect about acids and bases. So the first definitions we're going to look at are Arrhenius. So an Arrhenius acid is a compound that produces H+ ions in a solution. When H+ ions bump into a water molecule, it will form an H3O+. So sometimes you'll see H+, sometimes you'll see H3O+. We use those to mean the same thing. So a monoprotic acid, well, mono means one, contains one H+ ion that can be released in solution. So HCl, it has one hydrogen that can be released. Diprotic, di means two, has two H+ ions that it will produce. So like H2SO4, and then triprotic can produce 3 H+ ions, like H3PO4. So monoprotic, diprotic, and triprotic are just letting us know how many acidic hydrogens a molecule has. Now some molecules, they have other hydrogens that are not acidic. For example, acetic acid is HC2H3O2. So these hydrogens, they're not listed with the acidic hydrogen at the front, so what that indicates is there's only one acidic hydrogen that will separate. These 3 hydrogens are going to remain intact. So most of the time the acidic hydrogens will be listed together, especially in inorganic chemistry. Once you get to organic, that's where it gets a little tricky, especially when you get into carboxylic acids and things like that. So an Arrhenius base produces OH- ions in solution. So an example would be like NaOH, because it'll break up into Na+ and OH- when you dissolve it in water. So Arrhenius acid produces H+, Arrhenius base produces OH-. So next let's move on to Bronsted Lowry. So H+ ions are also known as a proton because hydrogen has 1 proton, most of them have 0 neutrons, and 1 electron. So if you make it H+, we remove the electrons, so all you have left is a proton. So H+ is also called proton. That's where monoprotic, diprotic, triprotic, it's 1 proton, 2 protons like that. So Bronsted Lowry acids are proton donors. That means they want to take their H+ and they want to give it to somebody else. So like in this reaction right here, we have HCl plus H2O making H3O and Cl-. So what's happening here? Well, HCl is having to give its hydrogen to water, so water can become H3O, and once it gives its hydrogen away, it becomes Cl. So that's what my arrow is showing. Where's the hydrogen going? So since HCl is the donor, it is acting as the acid in this reaction. Bronsted Lowry bases, on the other hand, are a proton or H+ acceptor. Okay, so the acids donate the H plus, the base is accepted. So here, who's accepting it? Well, water is accepting it because see, it's becoming H3O plus. Now I know you're probably thinking, wait a minute, I thought water was neutral. It is neutral, but in certain scenarios, it can act as an acid or a base. And here it's acting as a base. So this would be our acid, and water is acting as our base. So let's look at this example. So here we have NH3 plus water making NH4 plus OH minus. So what's happening? Well, H2O is giving its hydrogen to NH3, so NH3 can become NH4. And once water loses a hydrogen, you're left over with OH minus. So in this case, water is the proton donor, so it's acting as the acid. And NH3 is the proton acceptor, so it's acting as the base. So here is an example of water acting as a base. Here's an example of water acting as an acid. But of course, water just by itself, as long as it's pure, is neutral. But in certain situations, it can act as one or the other. So next we have to talk about conjugate acid and base pairs. So I have the normal book definition, and then I have in parentheses the definition I like to think of in my mind. So a conjugate acid is the particle formed when a base gains a hydrogen, or like I like to think of it as an acid created from a base. A conjugate base is the particle formed when an acid loses a hydrogen, or I like to think of a base created from an acid. So when you look at a reaction, there's two ways to tell your conjugate acid and conjugate base. I'll show you both ways. Alright, so this was the reaction we just did, and so we decided HCl is giving its hydrogen to water. So since it's the donor, it's the acid. Since water is the acceptor, it's acting as the base. And so then when we get to this side, what you can do is look at what would happen if we went in the opposite direction. So that's what my orange arrows are showing you here. So if we started with this side and went backwards, where is the hydrogen going? Well, in that case, H3O would have to give its hydrogen back to Cl to make HCl and H2O. So that means now H3O is the donor. But because it was formed, notice how both definitions have the word formed in them. That means they're going to be products. Because it was formed, it is the conjugate acid. And now Cl is the acceptor, but since it was formed, it's the conjugate base. Okay, so it's still going to follow the same proton donor and proton acceptor definitions, but they've been formed. The other way is just know the definition. So it says a conjugate acid is the particle formed when a base gains a hydrogen. So here's the base. What would H2O be if it gains a hydrogen? H3O. There's your conjugate acid. Or a conjugate base is the particle formed when an acid loses a hydrogen. Well, what would HCl be if it lost a hydrogen? Cl minus. So there is your conjugate base. All right, and then one thing to know is H3O plus is just called the hydronium ion. Like I said, sometimes we use H plus, sometimes we use H3O plus. That's just when the H plus is bonded with the water molecule. So let's look at these. So it says write the conjugate base for the following acids. Okay, well what is an acid? An acid is a proton donor. So that means its conjugate base will have lost a hydrogen. But it's a little trickier than that because you also need to alter the charge. We are going to lose an H plus, which means I then need to change my charge. So right now HCl is neutral. If I take away the H plus, I'm left with Cl minus. Okay, because I got rid of my H plus, so now I'm left with Cl minus. Because of course a plus and a minus make neutral, but we've lost the H plus. All right, here I have HSO4 minus, so I'm going to remove the H. So if I take away one from the charge, I get SO4 minus 2 now. Like you just subtract one from your charge each time you take away a hydrogen. All right, here we have H2O. So you may think when you take away a hydrogen, you get HO, but we call it OH because that's your hydroxide. And of course, this was neutral, so if you take away a plus, then the charge would be negative. Okay, so when you're forming conjugate bases, you're going to remove one hydrogen, but also subtract one from the charge. All right, so you try the next one on the next slide. We're just going to do some conjugate acids instead. No, that was weird. I don't know why it went out of order like that. All right, so remember, conjugate acid, you're gaining a hydrogen, but don't forget to alter that charge. So maybe pause the video, try this one, and then we'll look at it together. So NH3, if it gains a hydrogen, will become NH4 It was neutral, but I'm adding a plus, so it becomes +1. All right, SO4 minus 2, if it gains a hydrogen, it becomes HSO4. But I'm going to add a plus, so -2 plus 1 is -1. And then HPO4 minus 2 would become H2PO4. And then, of course, -2 plus 1, because we added a positive hydrogen, is a negative charge. So hopefully you got those right. Usually the thing that my students struggle with the most is that charge. So make sure as you add or take away hydrogens, you also alter the charge. Oh, that one went out of order too. Oh well. Alright, so it says, which of the following are conjugate acid-base pairs? Well, when you look at the definition of conjugate acid and conjugate base, they all deal with losing or gaining one hydrogen. So when you look at two formulas and you're looking for a conjugate acid-base pair, they can only differ by one hydrogen. Nothing else. No more than one hydrogen. They can't differ by an oxygen, anything like that. Of course, the charge will differ too. But anyway, so let's look at these. So we have HNO3 and NO3 minus. So do those differ by one hydrogen? Yes. So that would be an example. Alright, here we have H3PO4 and PO4 minus 3. Well, this differs by 3 hydrogens, so it is not a conjugate acid-base pair. Alright, here we have H2SO4 and HSO3 minus. Now this one's tricky, because does it differ by 1 hydrogen? Yes, this one has 2 and this one has 1. But it also differs by 1 oxygen, so it's not a conjugate acid-base pair, so you gotta be careful. Alright, here we have H3PO3 and H2PO3 minus, so do those differ by 1 hydrogen? Yes, they do. Alright, and then last we have HCN and H2O. Well, those do differ by 1 hydrogen, but this has a CN and this has an O, so it differs by other things. So on this one, your answers should have been A and D. Alright, so let's look at how to label acid-base, conjugate acid, and conjugate base. So remember, the conjugates are going to be on the product side, so don't even worry about conjugates till you get there. Alright, so we have to look at what is happening with the hydrogen. So here we have CH3COOH and H2O. And it's making CH3COO, so in other words, we're missing this H now, and it's becoming H3O. So what happens is this, which is acetic acid, is having to give, sorry, this is an arrow, it doesn't look that good. It gives its hydrogen to water. So this is where you have to remember your definitions. So a proton donor is an acid, so this will be my acid. And then a proton acceptor is my base. So here's an example where water is acting as a base. So then, like I said, you can either focus on your definitions of knowing an acid turns into a conjugate base, a base turns into a conjugate acid, or you can look at what happens with the hydrogens again. So what I like to do is I like to do the hydrogen method. Okay, so then if I was going to go backwards, H3O would have to give that hydrogen back to acetic acid, because it's just acetate right now. Okay, so now that means H3O plus is the donor. So it's the acid on this side, but because it was formed, it's the conjugate acid. And see, it came from the base. The base turns into the conjugate acid. And because acetate is now the acceptor, it's the base, but because it was formed from an acid, it is the conjugate base. So an acid never turns into a conjugate acid, or a base turn into a conjugate base. It's always acid goes to conjugate base goes to conjugate acid. Alright, so maybe pause the video real quick and you try this one. You're just labeling your acid-base, conjugate acid, conjugate base. So let's look at it together. So here we're starting with OH minus and HOCl. Well, now we have OCl, so that clearly means something's happened to this, and H2O. So what's happening is this is giving its hydrogen to OH minus. So remember, an acid is a proton donor, so this would be my acid. And a base is a proton acceptor, so this would be my base. So then again, to do this side, I know it's going to be my conjugates. I like to focus on the hydrogen. It doesn't matter how you do it though. Alright, so now water would need to give the H back to make the HOCl. So now water is the donor, so now water is the acid, but because it was formed from a base, it's the conjugate acid. And now OCl is the acceptor, making it the base, but because it was formed from an acid, it is the conjugate base. And so again, the base became the conjugate acid became the conjugate base, just like that. It can get a little tricky, so you just got to practice these a little bit. Alright, so a substance that is amphoteric can act as an acid or a base. So the example that I showed you, these are two reactions from previous slides, where water was acting as a base and water was acting as an acid. That is an amphoteric property. Water is not the only thing that can do that. Any substance that can lose or gain a hydrogen is amphoteric. So for example, HSO4 minus. It could gain a hydrogen and become H2SO4, or it could lose a hydrogen and become SO4 minus 2. So HSO4 minus would also be an example of something that is amphoteric. So, last set of definitions we have to talk about. I know there's a lot, so remember, Arrhenius acid produces H+, Arrhenius base produces OH-. Bronsted Lowry acid is a proton donor, Bronsted Lowry base is a proton acceptor. If you know Bronsted Lowry, Lewis is the exact opposite. So Bronsted Lowry acid is a proton donor. So what's the opposite of a proton? Well, we'll say electron pair, alright? You can say electron, but it really needs to be two. So electron pair, and what's the opposite of a donor? An acceptor. Okay, so whereas a Bronsted Lowry acid is a proton donor, a Lewis acid is an electron pair acceptor. And a Bronsted Lowry base is a proton acceptor, so a Lewis base is an electron pair donor. So how will you know what's happening with Lewis acid and Lewis base? Well, if I give you a reaction, you have to find who has the lone pair. The lone pair of electrons can be donated. If a compound doesn't have a lone pair of electrons to donate, it clearly can't donate anything. So what's happening here is this pair of electrons is being donated to boron to form this bond. So since NH3 is the electron pair donor, it's acting as the base. And since BF3 is the electron pair acceptor, it's acting as the acid. So let's knock out this section assessment. So what are the properties of acids and bases? Well, for acids, we'd said 4 in the previous slides. It was sour, can be strong or weak electrolytes, change the color of indicators, and reacts with metals. And for bases, we said 3. Bitter, strong or weak electrolytes, and change the color of an acid-base indicator. Alright, for number 2, how did Arrhenius define an acid and a base? Well, Arrhenius said an acid produces H+ ions in solution. A base produces OH- ions in solution. Alright, so acids produce H+, bases produce OH-. So how are acids and bases defined by Bronsted Lowry theory? Well, a Bronsted Lowry acid is a proton donor. A Bronsted Lowry base is a proton acceptor. Okay, so Bronsted Lowry acid is proton donor, Bronsted Lowry base is proton acceptor. And then what is the Lewis theory for acids and bases? Remember, it's the exact opposite of Bronsted Lowry. So a Lewis acid is an electron pair acceptor, and a Lewis base is an electron pair donor. Alright, so last one, identify the following acids as monoprotic, diprotic, or triprotic. We have H2CO3, so H2 would be diprotic. Alright, here we have H3PO4, so that would be triprotic. Here we have HCl, so that would be monoprotic, because there's only one hydrogen. And here we have H2SO4, so that would be diprotic. Alright, so hopefully that helped you with those varying definitions of acids and bases and knowing the properties of each.